Good morning and welcome to this educational webcast presented by Promise Neurosciences. Our webcast is entitled Alzheimer's Disease, Light at the End of the Tunnel, and I'm the company's Chief Executive Officer who will be speaking today. On the video itself will be our Executive Chairman, Eugene Williams. Today's video slide presentation will give an overview of the exciting scientific discoveries that now help us understand the underlying causes of Alzheimer's. With this knowledge, we're better armed to develop specific therapies to stop this deadly disease. I hope you enjoy this 15-minute presentation, which will be followed by 10 to 15 minutes of questions and answers. And we have received a number of questions actually prior to the meeting, so I'll address these at the end. And now, let's watch the video slideshow.
Thanks for joining us this afternoon. Today we're going to be talking about a topic I think that you'll find very, very interesting and one that we think holds a great deal of promise. Alzheimer's, there's light at the end of the tunnel. This is a very short discussion. In the next 10 minutes, I'm going to try to summarize for you the result of work that involves thousands of people, billions of dollars over many, many years that has led us to what I think is a tremendous opportunity to change the course of life for people and families afflicted by this horrible disease, Alzheimer's disease. It's the scourge of this century. Now, my name is Gene Williams. I'm with a biotech company called Promise Neurosciences. We are involved in this fight. You know, we are playing a role, but the goal of this discussion is not to talk about Promise today. The goal is to talk about Alzheimer's and why we, I think among many others, are very bullish that we made tremendous progress. We built a great foundation as a community of biotech and patients and physicians, and we were going to be able to translate that into some pretty rapid progress that's going to give us some great hope for families afflicted by Alzheimer's disease. So what I'm going to talk about over the next 10 minutes or so is a perspective on what we've learned about the disease and why we think that there's a tremendous prospect of making a big difference in the relatively near term. First, a little bit of perspective on Alzheimer's disease. It really is the scourge of the century. And as you think about it, we as a civilization over particularly the last couple of generations have made amazing progress against infectious disease, then cancer, then heart disease. And that's had the wonderful impact of growing life expectancy around the world. But as life expectancy grows, what we're finding is the prevalence of Alzheimer's increases even faster. It's one of the fastest growing diseases right now in the Western world. Over 6 million Americans and Canadians have the disease now, but what we know about the disease suggests that as many as 40 million of it or more may be developing it right now. The disease takes long enough to develop that probably tens of millions are in the process of developing disease, and if we live long enough, it'll hit us. By age 80, 30% of us have clinical symptoms. Now, what that means in a very, very tangible way is if you're like me, a baby boomer, between age 55 and 70, in a couple, the odds are 50-50 that one of you is already developing Alzheimer's. Maybe your parents are in that bucket. The odds are 50-50 that one of them is already developing the disease. Now, the great news, the light at the end of the tunnel, is with our understanding of the disease, with our understanding of what drives it, we might have the ability to identify and stop the disease from ever developing into symptoms. That's the promise of where we are today. Now, let me show you a picture of your brain with Alzheimer's disease. Look at that picture on the right. There's a cross-sectional picture of the brain. The AD means Alzheimer's disease. And look at all of those dark black areas. What that represents is billions of neurons that have been killed by the disease. The picture on the left, which is a healthy, normal brain, has plenty of neurons with lots of connections and, very, very little black space, very, very little open space. And the one in the middle is MCI, that's mild cognitive impairment. When you first start to show the symptoms of Alzheimer's disease, already a tremendous amount of your brain has been rendered vacant by the death of many, many different neurons. So what we're trying to do is stop that process from happening. And fortunately now, after a tremendous amount of investment and scientific progress, we understand what drives some brains to the right through the death of billions of neurons over many years. And because we understand it, we can make a big difference. Now, the light at the end of the tunnel has been built on past investment, including many late-stage failures. I think there have been a lot of highly publicized, very expensive phase 3 late-stage clinical trials that have failed. But the other way of looking at that is it's built a multi-billion-dollar foundation of knowledge. In addition to the failed studies, we've had ongoing registries and other clinical studies, a tremendous amount of investment in science. And what we're going to summarize today, and it's a very brief summary, is the consensus that now exists about what drives disease, which gives us a very clear picture of how to stop it. Insight number one. Takes many years, many years of your neurons being killed by toxic agents before symptoms start. For about 10 years, we have what's called prodromal disease, where the disease is progressing, toxic agents in your brain are killing neurons, but you don't show any symptoms yet. That's partly a testament to the brain's amazing resiliency and the ability for the brain to either reorganize its function or for biologic mechanisms in the body to fight back. But eventually, the toxic agents, the neurotoxic agents, start winning the war, and you show the first symptoms of mild cognitive impairment. But by that point, as you saw in the picture, already a lot of your brain has been eroded away. A lot of those neurons have been killed. The process just spirals out of control, and that's how you eventually get to that state of Alzheimer's disease, where you have tremendous trouble cognitively. I remember when I ran into my grandmother who'd forgotten who I was. We've all seen probably Alzheimer's disease in its most frank form, and what we're hoping to do is stop that from ever happening. What we know, insight number one, is that starts many years before you get to that stage, which offers hope of identifying it early and stopping it from happening. Insight number two that gives us great hope on that dimension is prions drive disease. Now, probably many people have heard of prions, misfolded proteins like mad cow disease or CJD that can transmit from animals, proteins that act like viruses and spread in the body and cause harm. Well, it turns out that, as we've studied neurodegenerative diseases, such as Alzheimer's, Parkinson's, ALS, and others, what we've come to realize is that a very similar process is going on in driving those diseases. Misfolded, propagating versions of proteins like beta amyloid and tau and alpha-synuclein are the bad actors that drive those diseases. Propagating means that they spread like a virus. The presence of a misfolded protein causes other proteins of that type to misfold and themselves become toxic. So very analogous to a virus. Now, what's great about where we stand today is a much better fundamental understanding of how that process evolves and therefore what we can do to block it. And what I'm going to do over the next few minutes is take you through the road from amyloid precursor protein to broad neuronal death and cognitive decline in a way which is pointing us as a community to how we stop that process from proceeding and create a very different future for people who have or may develop Alzheimer's disease. So amyloid precursor protein is a protein in the brain that has certain functions like developing synapses, the connections between neurons, or maintaining neuron health. But like all proteins, it breaks down over time. What happens then is amyloid precursor protein, among other things, secretes beta amyloid monomer. Now, you may have heard of beta amyloid. It's been identified, associated with a driver of Alzheimer's for a long time and a target of many of the late-stage studies that have failed. The beta amyloid monomer, interesting enough, actually has its own biologic activity. We thought for a while that it was nothing but sort of debris from cellular processes, but it turns out actually that beta amyloid monomer can help the brain in defense against microbial infections. But it also has its downside, which is it can develop and progress into a form of a neurotoxic prion that causes the disease. Beta amyloid monomer just means a single strand of beta amyloid wants to aggregate. When you put it in a test tube, it'll aggregate, it'll join with other single strands and form aggregates. Now, what we know today is that can go one of two directions. Either beta amyloid can combine in structure in a way that's inert. Like one of the things that was very puzzling early on in the billions of dollars of research that led us to where we are today in our understanding is in healthy normal brains, in an autopsy, often we saw beta amyloid plaques in patients who had no symptoms at all. So that raised the question of, gee, were we right? Was beta amyloid a bad actor? Or what else was going on? Well, what we know today is when beta amyloid monomer aggregates, when it combines with other monomer, it can go in an inert direction, which can lead to plaques that have no neurotoxicity, but also it can go into a neurotoxic form, a prion form. And by prion, we mean a protein that propagates or it spreads itself and causes harm, in this case, neurotoxicity. Now, what we further know is the way propagation works, the way that spreading works is the following. It's been shown in many different independent studies that in the presence of misfolded, propagating neurotoxic forms of beta amyloid monomer that wants to aggregate aggregates in that neurotoxic manner. The presence of a bad apple turns the whole crate to a bad apple, if you will. And this is the process by which prions propagate. In their vicinity, other proteins that might otherwise have been healthy misfold and also take on that toxic form. And that propagation continues. As the prions of beta amyloid aggregate into a neurotoxic form, they form fibrils, which are the fibrous bundles that sort of turn into plaques. They're directly neurotoxic. Or they form oligomers, which is a combination of different monomers, 2 or 3 coming together. Both of those are directly neurotoxic. And they continue the process of recruiting beta amyloid monomer, which is constantly being produced in the brain as amyloid precursor protein breaks down. And that's essentially creating 2 very, very aggressive armies attacking your neurons. But then a secondary effect happens. Probably many of you have heard about tau protein. As beta amyloid prions become present in the brain, they also start to catalyze tau protein misfolding, and the same process goes on. Misfolded versions of these proteins recruit what might otherwise be healthy versions of proteins, they misfold, and 3 armies attacking your neurons gather force over time, and eventually it breaks through the capabilities of your brain, like microglial cells, to clean up the debris. It breaks through the capabilities of your brain to be resilient in terms of loss of function, and then finally you have those horrible, devastating clinical consequences of Alzheimer's disease. After many years of neuronal death, you get that cognitive decline. Now, recently at an Academy of Neurology meeting just a few weeks ago, there was a very strong consensus that what we've learned from the decades of work by many dedicated people and billions of dollars is this is fundamentally the process that's driving Alzheimer's disease. Now, remember those pictures, from the healthy brain on the left to the mildly cognitive impaired brain on the middle and the frank Alzheimer's on the right. Look at all that black space growing. We know now what creates that black space is the death of billions of neurons, and what causes the death of billions of neurons are these misfolded versions of beta amyloid and tau. That's what we know. And because we know that, we now have a much, much more refined idea of what we need to do to stop that from happening. In fact, this is a topic for another day, but we can identify specific prions in a specific patient in a way that allows us to block those specific prions, the different prions of beta amyloid, different prions of tau. And we have the capability now, which is offering some tremendous promise for where therapy can get to in a relatively short period of time to be much, much more effective and fundamental in the way we're addressing Alzheimer's disease. So let's talk about, what that future of therapy is shaping up to be. The future of mental clarity is clarifying. Foundation therapy will be prion blockers. We know now, with a high degree of confidence, what initiates and drives this disease. And we understand the biologic processes that make that happen, and we're getting very, very close to having ways of identifying it and blocking it for patients. But we also have a number of other therapies in development that in combination could really make a huge difference. And I think that we've seen many chronic diseases where there's not a single magic bullet, if you will, but the combination of different approaches, each of which comes from, brilliant scientific work followed by, millions and millions of dollars of investment leads to an armamentarium of therapies that finally make a huge difference in a disease. Look what happened in HIV, for example. Look what's happening in cancer. So as we look forward to, the future of Alzheimer's treatment, with that foundation therapy of prion blockers, we'll have plaque-busting therapies that break up existing plaques of beta amyloid and tau. We'll have therapies that enhance the microglial function that kind of reactivate the ability of your brain to clean up the debris and start winning the war back. There are approaches to beta secretase, for example, which kind of dampen down the production of beta amyloid and create fewer recruits for the toxic armies to bring into their battle against your neurons. We're also working at an earlier stage on restoring mitochondrial function and reducing neuroinflammation. But I think the bottom line here is that we expect to have in development, we already have in development, a number of therapies, and we understand now the biology well enough that I believe the ability for us to dramatically modify the course of disease or stop symptoms from ever happening is on the horizon, and that's why there's light at the end of the tunnel. So to summarize, we have a very cautiously optimistic point of view. I think all of us who've been in drug development for a long time recognize just how challenging and hard it is, but we also recognize when we're getting to a point of understanding a disease well enough that there really is the prospect of changing it dramatically. And that's where I think we are, that's where we believe we are in Alzheimer's disease. We have a multi-billion-dollar foundation of knowledge that's been built over decades. We're leveraging that. It's painted a picture of what drives disease and how we might deal with what's become the epidemic of this century. Prions drive disease. These misfolded neurotoxic beta amyloid and tau molecules kill neurons and erode the brain. But since we know that, we are much, much closer. In fact, I think it's in the next few years that we will have a number of therapies that could stop that process from happening, which gives us a very clear picture of a future without the devastation of Alzheimer's. And we hope you all agree that it's time to act as fast as we can. And we hope this simplified version of what's going on and how we can see a different future helps with that. Thanks very much for your time.
All right, now that you've seen the video and slide presentation, let's address some of the questions we've received. First question, there have been many expensive late-stage failures in Alzheimer's drug development, as alluded to in the presentation. So what's different now? Why should we expect a different outcome? This question is referring mainly to studies of products addressing beta amyloid in Alzheimer's disease. We now know many of the reasons for those failures, and are starting to see successes, early successes, when those causes are addressed. First, many of the early studies included patients who either did not have Alzheimer's disease or may have had Alzheimer's or symptoms of Alzheimer's, but didn't have beta amyloid-driven Alzheimer's disease. So all the studies we do make sure only to include those appropriate patients. Secondly, many early trials included patients with advanced symptoms. We now know that at the point where symptoms are occurring and advanced, there's already been very substantial neuronal death, and it's very hard, if not impossible, to see a benefit in a clinical trial where so much brain matter has been destroyed. Now studies focus on showing a benefit in patients at an earlier or very much earlier stage when very minimal signs are present. Going forward, we expect to see further improvements, including only the right patients in clinical trials. We now know that there are several distinct strains of neurotoxic beta amyloid. We're developing the ability to test which strain a given patient has and to develop therapies that target that specific neurotoxic strain of beta amyloid. In the future, we expect to be able to design clinical trials that only include patients with a specific neurotoxic strain of beta amyloid and then treat them with therapies targeting that same specific strain. These trials are likely to have much greater odds of success than earlier trials and probably easier to manage because the trial numbers would be smaller as well. This approach is called precision medicine and has been associated with significant improvements in the way we treat numerous diseases, like cancer, for example. Another question here we received about prevention, and you say now that we know the disease process and neuronal death starts long before we develop symptoms. Does that mean we can think about preventing Alzheimer's? Well, the short answer is yes, but not immediately. First, we have to show that the therapies work in very early disease. But once we do that, the next step can be to treat to prevent. A leader in the field, Risa Sperling at Mass General, has called this the prevention paradigm, and ultimately that's the goal we want to reach. What it will take is clear measures of biologic progression of disease. Prevention means we don't have symptoms to tell us that the patients have disease and need treatment. Now that we know that prions are driving the disease, and in fact know that there are different strains of these toxic prions, we're in a position to diagnose disease progression before symptoms arise and prevent it. Think of cholesterol as an analogy. It's a very good one. We measure high cholesterol and provide therapy to lower it, and know that this lowers the risk of heart attack and stroke. In Alzheimer's, we can see the same model. If we screen for the prions, these toxic prions, then also look at imaging like PET scans, for example, see if there is evidence of plaque buildup, we could imagine having enough evidence to start treatment, monitor progress, and avoid ever developing symptoms, a true prevention model. This is absolutely the goal, and the current advances in precision medicine now make this possible. One more question, also on precision medicine. We mentioned the idea specific to the patient was alluded to previously in the presentation. Could you elaborate? What does this really mean? Well, precision medicine is fundamentally based on the insight that we have historically defined disease based on symptoms, but that the biology driving disease is actually much more complex than its symptomatic expressions. In the past, we've talked about heterogeneous diseases. Some Alzheimer's patients have symptoms that progress rapidly. Others do not. Some have symptoms that occur earlier in life or later and progress rapidly or slowly, depending on the patients. Some patients develop aggressive behavior, others don't. So you can see it's a very heterogeneous disease. What we know now is that our old diagnostic categories are really bundles of similarly related but distinct disease entities. The exact pathogen or toxic agent driving the disease then varies. It makes common sense, right, that the more precisely we target the disease-causing pathogen, the better the results will be. It's like a targeted smart bomb versus World War II carpet bombing. In Alzheimer's, numerous recent publications have shown that there are distinct strains of the neurotoxic prion, i.e. patients with Alzheimer's symptoms actually may have one of several slightly different diseases. So what we're working on now is creating the ability to identify exactly which form of disease a patient has, which specific neurotoxic strain of the misfolded protein, and then give them targeted treatment that attack that specific neurotoxic form of beta amyloid or the protein called tau. We expect this may result in significant improvements in therapy. One more question here. In the presentation, you mentioned both beta amyloid and tau. Which is the most important in treating Alzheimer's? Do we know? Well, this is an important debate. We believe, and many experts in the field also believe, that the answer is both are important in different patients. It appears that neurotoxic prions of beta amyloid seem to start or occur first and catalyze in some patients the development of neurotoxic tau. Later in disease, it may be that tau is doing more damage, but both contribute to the progression of disease. So we believe the most important therapy is patient-specific. We need to measure what neurotoxic prions a patient has, beta amyloid and or tau, and then specifically target those neurotoxic prions with specific therapy. This is precision medicine. Okay, one final question. I think we've all heard that there's a debate about whether beta amyloid is cause or consequence of disease. Where's the truth here? What is our view? Well, that debate arose as people tried to understand the failures of early trials. That debate has died down quite a lot now, because we have an understanding of better trial designs and are seeing some initial successes in addressing patients with early stages of the disease. The other factor that contributed to that debate was the fact that autopsies sometimes showed beta amyloid plaques in patients who had no symptoms. What we believe now is that beta amyloid can aggregate in an inert form, and this was briefly presented in the presentation. The right perspective is that certain forms of aggregated neurotoxic beta amyloid prions are a primary driver of Alzheimer's disease. So I think that covers largely the type of questions we received. And again, would like to thank everyone for their presence and wish you a good day. Thank you.